Okay, what we are going to start today is the third chapter, which is probability. Okay, so we are going to talk about the topic probability in detail in this chapter. So probability is a topic which is one of the most interesting topics in statistics. It is very related to our day-to-day life. Even without knowing that it is probability, we use it a lot. Okay, every day, all the time we use probability in our day-to-day life. It is very attached to our usual proceedings, the things that we do in our daily life. But usually we are not aware that we are using probability concepts. So this is very applied, very applicable in most of the situations. And the interpretations are nicely done, and probability is a widely discussed topic in statistics, and a lot of theories, a lot of concepts have been built based on the concept of probability. And so this actually came in during wartime, long time ago. The two mathematicians, Fermat and Pierre, they came up with this nice interpretation of probability. They are actually playing a certain game. That game, the winner will be decided at the very end. So you have to wait until the end of the game to decide who's the winner and who's the loser. So you bet certain money and you play the game. But you cannot, if you have to interrupt the game somewhere middle, you do not know who's winning now, right? Or who's losing. You cannot figure it out. But during these war times when people are playing, suddenly there will be an attack and you have to stop everything and run. So you do not know where the game is going, and you do not know how to divide the money that you have put on the game. So whether you have to divide it equally, if one person is winning, and that person should get more money, right? Not the equal amount divided into two parties. So that problem was the basis for this probability. So they wanted to know, if you are going to stop the game at some place, you want to calculate as a number what is the chance of winning, let's say, player 1 and player 2. Okay, so if the winning is say 100%, any person who exceeds the chance of winning more than 50%, that person has higher chance of winning at the end. But you do not know what will happen in between. But at that point that you have to interrupt the game, one person has say 75% chance of winning. So that person should get more money. Other person has only 25% of winning. So that person should get only 1/4 of the money. So something like that. So based on this application, this game, deciding the winner, Fermat, they came up with this idea or concept of probability. So if you put this into something explainable, probability, we can say this is the mathematical explanation of chance. Because we talk about chance a lot in our day-to-day life. Like, what is the chance of rain today, right? What is the chance of winning a lottery? What is the chance of getting an A for a certain course? Okay, you think about this, right? So this chance is actually the probability. Okay, so you look at the in the news, the meteorological department, they give you signs about the thunderstorms and things like that, and they give you they say as a percentage, there's 90% chance of raining today for these provinces, right? So how do they calculate it? Based on certain information, using some mathematical models, they calculate as a number. So that is the mathematical explanation of chance, right? So when it comes to statistics, in order to calculate the probability or explain this chance mathematically, you have to learn few keywords. Okay, so we start with the first keyword, which is called the experiment. Now, when we say experiment, probably the word that will come into your mind is the experiments that you conduct in laboratories like physics, chemistry, botany, zoology, right? You do experiments, right? You know, mixing certain liquids together, what will happen, what is the precipitate, what the color changes, things like that. Or in physics, you take the prism and, you know, put a light inside it and look at the colors, you know, things like that. So those are the deterministic experiments. So there are two types of experiments. Experiment is any process of observation or measurement that has well-defined set of outcomes. Okay, you also have well-defined set of outcomes. And there are two. The deterministic are the experiments that we usually conduct in laboratories. So this is the experiment that you are very familiar with. Okay, you conduct in laboratories to verify certain laws of science. Say, experiment to verify the Newton's law of motion. Okay, you can do that, right? If you want to show the PV equals nRT equation, the verification of that, you can do a you know, using certain elements, you can do, or you can make an experiment inside in a laboratory. Okay, but at the end, you actually know that the outcome. Okay, you know, when you prove the Newton's law of motion, you know, you'll get the G, the constant value of G. After some calculations, you can get that value. But you know that, okay, that value is there. You are just doing the experiment to verify it. Okay, and you know the PV equals nRT. You are just doing the experiment to verify it. Okay, so you already know the answer. But what you are trying to do in deterministic experiments is, you know the answer, you are trying to prove that you can do it in practical setup. On the other hand, the random experiments, so these are the experiments we are going to talk about in probability. The probabilistic or random experiments. Those are the experiments where the results are uncertain. That means you do not know what will happen at the end until you finish the experiment. So this is very different than the first one, the deterministic one. In deterministic one, you know the answer. You are trying to verify it. On the other hand, in random experiments, you do not know the result. It can be one out of many. Okay, so there are more than one possible outcomes, and so you're after you finish the experiment, only you know, okay, this is the answer. Say, for example, when you toss a coin. Before you toss the coin, you do not know whether you will get head or a tail, right? You do not know, but you know it will be head or tail. So those are the possible results that you may get. But until you toss the coin and look at the answer, you do not know whether it will be a head or a tail. Okay, so tossing a coin is a random experiment. Another one is the rolling a die. Okay, so usually if you think about the six-sided dice, you have six possible outcomes, 1 through 6. Until you roll it, you know, shuffle it and roll it and look at the face up, you do not know what will be the answer. Okay, but you know it will be one of the answers from 1 to 6, right? So those are the random experiments. Random experiments are whose result is uncertain, but it will be only one outcome among many possible outcomes. Okay, so I hope it is clear what is a random experiment and deterministic. So when you talk about probability in statistics, what we are talking about is only the random experiments. We don't care about the deterministic. Okay, there's no meaning in calculating probabilities when you already know the answer. So in statistics, we look at these random experiments. So we talked about the outcome. So what is an outcome? That is the result obtained from an experiment. So this outcome can come in many forms. It can be an instrumental measurement like length, weight, speed, temperature, rainfall, okay? Or it can be yes or no answer, or 1 or 0 answers if it is categorical, okay? Or maybe it is after doing a certain calculation using some, like you calculate the BMI, okay? You need the weight and the height, and then you calculate the BMI. So that is after certain measurements and using an equation you calculate, okay? And if you think about variables, your outcome, these variables can be categorical, continuous, discrete, all those possible types, okay? So you have these outcomes, and if you put all these possible outcomes together for a given experiment, you call it the sample space, Okay, so sample space is the set. So when you see set, this is the set defined in mathematics. Now the set operations, what we call in Sinhala Kulaka. I'm sorry, I'm not familiar with the Tamil word. The set of all possible outcomes of an experiment is called the sample space. Usually we denote it using S or omega. Okay. And each and every outcome of a sample space is called experiment or a sample unit. Okay. So when it comes to sample space, it can also come in many different ways. Okay. Usually you can list the elements in your sample space. If it is not a lengthy one, you can list them. Okay. So if it has a finite number of elements, you can list them nicely. Say for example, see the first example. Sample space for the possible outcomes of one flip of a coin. If you flip a coin, just one flip of a coin, how do you write the sample space? So I'm going to use S throughout the lesson to define the sample space. If it is a set, you know you have to write the values within curly brackets. When you flip a coin, what are the possible outcomes that you can get? It will be either head or tail. In set notation, you divide these different outcomes using a comma. So this is how you write the sample space. It is a set, so you have to write the element inside curly brackets and you have to separate the elements using a comma. If there are repetitions, we do not include the repetitions. In sets, you don't have repetitions. Okay, so only once. So this is the sample space of flipping a coin. Now, the way you define your sample space, it depends on the problem at hand. Okay, so here's another one. If an experiment consists with one roll of a dial, and we are interested in which face is turned up. Now, what will be the sample space? So, so this is a 6-sided dice. Okay, if you think about 6-sided dice, what is the sample space? Can someone tell me the sample space? Is the all possible outcomes you can get if you roll a die, 6-sided die. Yes, what are the outcomes? You can unmute and answer. Anybody? What is the sample space?
1, 2, 3, 4, 5, 6.
Yes, 1, 2, 3, 4, 5, 6. Thank you. So that is the sample space. But if you are interested only in whether the face turned up is even or not, even or odd, so what is the sample space in that case? So you don't care whether it is 1 or 2 or 3, it doesn't matter. What you are looking at is whether it is odd or even. So what is the sample space now? Either odd or even, right? So see, it's the same experiment, but the way you define your the objective of the outcomes, your sample space can be different. Is that clear? If you have any question, please stop me and ask, okay? Right. Okay, now look at this example. This is a little bit different. Sample space that might be appropriate for an experiment in which we roll a pair of die, one red and one green. What do you think about this one? Now you are rolling 2 dice, pair of dice. One is red, one is green. Again, think about 6-sided dice. So let's say X represents the number turned up by the green one and Y the red one. Now, how do you express that sample space? Okay, so each of these dice, they have 6 sides, 1 to 6. So what are the possible outcomes? Now we are rolling both dice together, right? Now, first of all, can someone tell me how many outcomes are there? Now, in the previous example, if you roll a die and which face is turned up, there are 6 possible outcomes. If you are checking only odd or even, you have only 2 possible outcomes. In this example, when you roll one red dice and one green dice and looking at the answer, how many possible outcomes are there? How many possible outcomes are there?
12.
Try again.
36.
36, yes, because you have 6 and 6. All of these 6 should have combined with each other. So there should be 6 times 6, which is 36. So how do you write them? Okay, so if it is x and y, right? So if you think the xy pairs, you can get 1, 1, 1, 2, so likewise up to 6, 6. So all 36 possible pairs. Now sometimes it is easy if you draw the sample space like this. Okay, you don't have to write the set notation like this because it's not easy. If you do it like this, this is also okay. So let's say my x is the green one, right? And y is the red one. So x can have 1, 2, 3, 4, 5, 6. This one also has 1, 2, 3, 4, 5, 6. So you can easily find the combinations. 1, 1, 1, 2, 1, 3, 1, 4. So you can make sure you don't miss any combination. So this will be 2, 1, 3, 1, and so on, all the way up to 6, 1. So this will be 2, 2, and so on up to 2, 6. Okay, so you can continue this. Here you get 3, 3, 4, 4, 5, 5, 6, 6. I'm not going to fill everything, right? So you can do this. You'll end up with all 36 possibilities. Is this clear to all of you? Right? So when you say 1, 1, that is green has 1 and red has 1. So when you see 1, 4, okay. So this is red is 1 and green is 4. Okay, you can see the pairs, right? So this is 3, 1 means red gave 3 and green gave 1. Okay, so likewise you can get the sample space. Okay. Now again, there's another way to classify it as finite and infinite sample space. Okay, if your sample space contains finite number of elements like the previous one, 36, okay, then it is a finite sample space. So you know exactly the number, okay, how many will be there. But what if your experiment is you flip a coin until head appears? Then how do you write the sample space? You flip the coin until head appears. So you do not know, maybe the first flip you get a head, then you stop. Or maybe it is the second flip that you get the head, then you stop. Maybe you have to flip 10 times to get the head. That is all first 9s are tails. So you do not know when you have to stop. Okay, that means it is infinite. So it goes on, you do not know, but it is countable, but you do not know the exact number. So how do you write in the sample space in that case? It can be 1, or it will be, it is easy if I write it like this, TH. That is the first one tail, second head, then you stop. Or first one, second one tail, third head. Or TTTH. It will go on like this. Fourth and head. It will go on like this. We do not know when it's going to stop. Who knows? Maybe you have to flip 50 times to get the first head, right? So this is called an infinite series, okay, or infinite sample space, okay. Now in this course, we are not going to look at this infinite stuff. We are only looking at the finite sample spaces, okay. So we learned about the experiment. We learned about the outcomes. We learn about the sample space. Then the next keyword is called the event. An event is the subset of your sample space. Okay, so it is a subset of your sample space. Okay, usually we denote them using capital letters, capital A, B, C, and so on, or W, X, Y, Z. Okay, say for example, suppose this is your sample space, that is rolling a dice. Sample space is from 1 to 6. And we define a certain event A. Okay, so this is our event A. It is our event A is defined as the numbers divisible by 3. So out of the values in your sample space, you define a certain event. That event A contains only the outcomes which are divisible by 3. So what are the values divisible by 3? It's only 3 and 6. So your A is 3 and 6. So you can see that this is only a part of your sample space. See, 3 and 6, it's only 2 elements out of it. So this is a subset. Okay, so A is a subset of your sample space. Okay, so let's try another one. Let's define our event B as getting an odd number. Can someone tell me what is the event B? So I see it is a subset, so you have to use the set notation and write down the elements inside it. So what are the values that event B can contain?
1, 3, 5.
1, 3, and 5. Yes. In the same manner, let's say C is getting even numbers. So what is our C? C will be
2, 4, 6.
6. Okay. Right. So likewise, you can define your events. Okay, so you can see the sample space is there, which contains all possible outcomes of X experiment. And then if you take only subsets out of your S, we call them events. So you can define several events, okay, as you want for a given experiment. Right. Okay. Now let's go back to the example where we were rolling 2 dice, a pair of dice, the green one and the red one. Okay. We are going to define an event, let's say event B, the total value of points rolled with the pair of dice 7. How can you do that? So start with the sample space and see whether you can find it. Okay, so I'm writing the sample space. I think we had the green one at the top. Okay, so let's use the same. Here's the green one, and then we have the red one. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So what do we need? An event B can be defined to be the total value of points rolled with the pair of dice is 7. The total should be 7. Now, rather than writing all possible outcomes, shall we write down the total points where you can get 7? How can you get 7? You can get 1 and 6, right? You can get 1 and 6. This is 7. Then 2 and 5, 7. Okay. So you should get the total value is 7. What else? 3 and 4, 7. 4 and 3, 7. 2 and 5, 1 and 6. So these are the possible ways that you can get 7. What are they? 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. Now you have to be very careful. 1 and 6 and 6 and 1, are they same? 1, 6 and 6, 1, are they same? First and the last one? No. When you say 1 and 6, okay, so that is red giving 1 and green giving 6. But when you say 6 and 1, that is red giving 6 and green giving 1. So those two are different. right? So altogether, how many outcomes are there? In event B, only 6 outcomes. Can you see that? So how do you write B? So our event B is now, you can write down these combinations. These are the values that we can get where the total is 4. So again, remember 1 and 6, 6 and 1, they are not the same. 2, 5 is different from 5, 2. Okay. So here's our B, and it has 6 outcomes. Okay, is this clear to all of you? Right? Any questions? No questions? Okay, so let's try another one. Let's say I'm going to define event W. The total is, okay, so our total is greater than or equal to 10. Greater than or equal to 10. What are the possible outcomes? The total should be greater than or equal to 10. Can someone tell me? W? Any answers?
5.
Yes.
5.
5, 5. And then
4 and 6.
4 and 6. What else?
5 and
6 and 6.
6 and 6. There are some more. What about
5 and
6.
6.
Yes. 5 and 6, which means 6 and 5 is also there, right? Anything else? No, right? So you have 5, 5, which is 10, 4, 6, which is 10, 6, 4, which is 10. Then you have 5, 6, and 6, 5, which are 11s, and 6, 6, 12 is the maximum we can go for. So there are again 6 possible outcomes. Okay? Right. And I'm going to define my next event as Z. My event Z is both dice give same value. Both of them will give you the same value. Now what is Z? Now this is easy.
One,
1, 1,
2, 2,
2, 2, and yes, you know, there is 3, 3, 4, 4, 5, 5, and 6, 6. So those are the diagonal values, right? So likewise, you can come up with many different events and then figure out the outcome. When you have the sample space written correctly, it is very easy to answer any, or find out any event, the outcomes of any event defined using that sample space. Okay. So whenever you see the experiment, make sure you write down your sample space correctly. Okay. After that, calculating probabilities, identifying the elements for each event, it's very easy. And you will not end up with any mistake. Okay. Right. So there are a few other events. C defined as total values less than or equal to 5. D, both dice given the same value. We already did it. Okay. So this is Z. You can try this one. Okay. You can try this one. Total value less than or equal to 5. Right. Okay. So here's another example. Consider an experiment that tossing 3 coins simultaneously with the intention of observing the faces that tossed up. Okay, so how many coins that you are tossing now? 3 coins simultaneously. So at the same time, you are flipping 3 coins. Okay. And here are the events that you have to identify. Event A is getting 2 heads from the experiment. B is getting 3 heads from the experiment. C is getting at least 2 heads. Now, how do you find these outcomes? So the first thing you have to do is find your sample space. 3 coins tossed together. Okay. So let's start it right in the sample space. Head, head, head. All heads. Head, head, 1 tail. Let's write down all possibilities where you can get 2 heads and 1 tail. Okay. Then next you have 1 head and 2 tails. And finally, all. Okay, so this is the all possible outcomes you can get when you toss 3 coins together. It can be all 3 heads, first 2 head, next 1 tail, first 1 head, second tail, third 1 head, and so on. So likewise, all the way up to all 3 tails. So here's your sample space. Now, can you find what is A, what is B, and what is C? Right, so let's start with A. Getting 2 heads from the experiment. Getting 2 heads. So you have to look at the sample space and pick all the elements where you see 2 heads. So here's the first one, here's the first one, here's the next one, the second and third. So how many possibilities are there? Getting 2 heads? Only 3. So you have HHT, HTH, THH. Okay, next, getting 3 heads from the experiments. 3 heads, you see this is only 1. All 3 heads. Try to write it like this. C, getting at least 2 heads. What does that mean? At least two heads. The least you can get is 2 heads, or it can be many. Right? So how do you write that? At least 2. So you have to write all possibilities where you can get 2 heads. And then what is the other possibility? All 3 can be heads. Okay, so at least 2. At least 2, or it can be 3. Right? So this is how you find elements in an event by looking at the sample space. Okay, is this clear? Any questions so far? Okay. Right. Okay, now let's look at some interesting combinations of events or special cases of events that you can come up with by combining 2 or more events together. Okay. Now you have learned these things for mathematics. I think usually we learned it in grade 8 or 7, the union, intersection, and complement. Okay, so these are the 3 main combinations of events that we are going to look at. Okay. Now, in order to define this union, intersection, and complement, let's define 2 events A and B for a given sample space S. Okay, so we have 2 events A and B for our sample space S. Okay, so the union of A and B, we write it, here's the notation, A union B. Okay, that is the subset of S that contains all the elements that are either in A, in B, or in both. Okay, so be careful. Either in A, in B, or in both. Okay, so I'll use the Venn diagram to explain this. So I'm sure you have you're familiar with the Venn diagrams. Okay, so here's usually the sample space is drawn as a rectangle and events as circles inside it. Okay, so this circle is for event A, this circle is for event B. A union B is where you have elements in A or B or in both. Both is where they intersect. Okay, so this is called the A union B. And sometimes we call it A or B. Right? So the union contains all the elements either in A or B or in both. Okay, then comes the intersection of A and B. So here's the notation A intersection B. This is the subset of the sample space S that contains all the elements that are both in A and B, both. That is the overlap. Or you may say the common elements or common outcomes. How do you draw it? In the Venn diagram, here's my sample space, the rectangle S. And these are my events, A and B. This is the place they intersect. That means the overlapping area. So what do you call this? A intersection B. And sometimes we call it A and B. O is for union and E is for intersection. Okay. And next comes the complement of A. Usually we denote it as A prime, or sometimes we use AC at the top for A's complement. Okay. That is the subset of the sample space that contains all the elements in S that are not in A. So this is sometimes called not A. Okay, all the elements in S but not in A. So how do you write it? So here's our sample space A. Sorry, the event A. Everything in S but not in A. So this is how you color it. All the elements outside. So this outside is the A's complement. Okay, so I guess this is clear, the union, intersection, and the complement. Okay. Now next we have something called the mutually exclusive events. We usually use ME, mutually exclusive. What are they? Suppose you have two events where they do not overlap at all. Something like this. So do you see anything common to these A and B? No. Okay, so this is a mutually exclusive. A and B are mutually exclusive, which means their intersection is empty. Okay, so this is the empty set. Or you can write A intersection B is empty. Empty set, nothing is there. Okay, then we call they are mutually exclusive. Or you can use there's another word which is called the disjoint. Disjoint events. Okay, you see they are not joined together, right? Okay. So see, you have that A intersection B it's empty. So these are the disjoint events or mutually exclusive events. The next one is the A contains in B. Okay, that is A is which means A is a proper subset of B. What does that mean? Okay, so here's my sample space. It says A contains in B. So we have B and A is somewhere inside B. So this is what we call A is contained in B. Okay, A is a proper subset of B. Okay, so now if you go back to this union, intersection, and mutually exclusive events, can someone give me an example for mutually exclusive events from the examples we have already discussed? Can anyone remember? We already, from the examples we already discussed, sample space and then the two events such that they are mutually exclusive.
Tossing a coin.
Tossing a coin, head and tail, yes, you cannot get them together. Okay, that's one example. Another one? Okay, when you roll the dice, 1 to 6, can you come up with two events which are mutually exclusive? Think about the numbers 1 to 6. Events, two events that do not have any values in common. We actually discussed it.
Getting an odd number or an even number?
Yes, odd and even. Okay, you never get, there are no numbers which are both odd and even, right? So both odd and even numbers, they are disjoint events, right? Okay, so likewise, you can come up with examples. So think about them, okay? So you have we talked about the complement and then the proper subsets and everything. Okay, so let's look at an example, right? And see whether you can understand or you have understand this intersection, complement and union. Okay. Right. So I have given the sample space A, B, C, D, E, F, G. And the two events A, B, and C. A is A, B, C, D. B is A, C, E, G. C is E, F, G. You have to find the following events, right? Now look at these the sample space and events and try to find the answers, A to G answers, right? So I'll start with the first one, A's complement. The first one is A's complement. How to write A's complement? All the elements in S but not in A. So what is that? Not A. A, B, C, D, everything other than that, E, F, G. Okay. So likewise, can you fill B prime, B's complement and C's complement? Okay, Sampath, 1648. Can you tell me what is B's complement? Yes, Sampath, are you here? Yes.
ACEG.
ACEG is B, yes. You need B's complement. See, you have this small tick at the top. So everything in S but not in B. What are they? Yes?
EFD.
B, F, D, right? Okay. And there was a question about 5, 5. Can you write it twice, right? Well, when you get red 5 and green 5, how do you differentiate it? Right? Both are 5. So you are not repeating twice. Okay. When you have the same value as the face, you don't repeat. Okay. Right. And then what is C's complement? Let's say 42. Gayan Nuanta. Can you tell me what is C's complement? C's complement. Gayan? Can you hear me? No. Well, if you're
Yes, madam.
Okay. Tell me.
C's complement is without E and without EFG and without EFG, other elements we can get.
So yes, they are A, B, C, D. Okay, thanks. Right, now can you find A union B? A union B. What does that mean? The elements in A or B or both, right? Okay, now compare A and B. You have A, right? So you can write A. You don't repeat in set notation. Now A is in event A is in event B also. So you do not write A twice. You write only once. That is a rule in set notation, right? Then you have B. B is in A. C is in both. D should be there. What else? E should be there. G should be there. So this is the union of A and B. A union B. So you have all the elements in A, all the elements in B, and even the overlaps. Okay, so here's our A union B, right? Now we have the A intersection C. A intersection C, what does that mean? Where they overlap. So do you have common elements? A, B, C, D, E, F, G. Are there any common elements?
No.
So it's the empty set, right? Now can you try B union C? Okay. B union C. Let's see. Akla Ashraf, can you tell me what is B union C? B union C.
EG.
EG, not the intersection, union. Union means everything in B, C, and then they are common elements. Okay, so this is the union, which means you have write everything in B and then in C also. EG is already there, so you write F. Okay, is that clear? Right. Next one, A intersection B's complement. Right? A intersection B's complement. So here's your A is there. Okay, here's your A. B's complement is there. Now you have to find their union. Can you do that? A union B's complement. How do you find it? Okay, compare A and B's complement. Sorry, not the union, intersection, right? Intersection of A and B complement. So what are the common elements? You have B and D. Okay, can you see that? B and D. Okay, right. Let's go to the next one. A union B, its complement. Okay, so see the difference between E and F. When it comes to F, you have a bracket and the complement is outside. So that means A union B and its complement. So first find A union B. You already have it in B. See, A union B is there in part B. Now get its complement. Complement means everything in S, but not in A union B. What are they? A, B, C, D, E, F. What is the element that is missing?
F.
F. So that is the complement of A union B. Right? Now let's move on to the last one. You need the intersection of A's complement and B's complement. You have A's complement, you have B's complement. Yes, A's complement. Yes, B's complement is there.
F.
So what is the intersection? F. Right? Now can you see there's a pattern here? Both F and G, they have the same answer. Now we'll come to that later. Okay, that's a rule. Right, okay. So is that clear to all of you? How to find the unions, intersections, complements? Right? Okay. Now if you want to draw this as a Venn diagram, can you do that? How do you put these values into a Venn diagram? Okay, so here's my sample space. You have 3 now. A, B, are there any disjoint events? A and C is not right. So let's see, this is A, B, C, something like this. Sorry about the drawing. Let's try a better way. How do you draw it? Hold on. Okay, we'll see whether you can fill it easily. Okay, so we have A, B, C, and D, and A intersection B is A and B, they have common elements. A and C. Okay. So A contains C and D. B contains E and G. Out of them, E and G are in C also. F is in C, A, C, E, G. Okay, so that's the Venn diagram. Okay. So C is not overlapping with A, right? So this is how we draw the Venn diagram, and all the letters, all 7 letters are there. 1, 2, 3, 4, 5, 6, 7 letters are there, right? So you should be able to draw the Venn diagram also, and you can see that there are no elements that are only in B. Let's see, this part is, it's empty. Okay, either B is joined with A or C, right? Okay. Any question from this one, this example? Okay, right. Okay, now let's try to calculate probabilities. So far, what we have learned is only the sample space, about elements, the outcomes, then events, and combination of events. Okay, now we are moving on to the topic probability, how we can calculate it. Okay, so when we say probability, say probability of event A. Okay, the probability of event A is calculated by counting the number of outcomes in event A divided by the number of outcomes in the sample space. That means how many are in A out of the total, right? So simply, the probability of an event is the number of outcomes in A divided by the number of outcomes in the sample space. So our notation is the probability of A. If it is event B, C, D, E, you can write the notation P within parentheses, whatever the name of the event. This is the number of elements in A divided by number of elements in the sample space. Okay, so this is how you calculate the probability. Now, there's something you should remember. Okay, so this is from the basic or the exact theory about probability. We have something called the law of large numbers. Okay, the law of large numbers. What it says is, I'll explain it using an example. Now think about flipping a coin. Okay, you already know this experiment, flipping a coin. Let's say you are flipping a balanced coin. Okay, flipping a balanced coin. Now you already know from, you have read about these things and you have done these experiments. The probability of getting a head or probability of getting a tail, what do you call? What are these probabilities? You already know this information. We call it 50-50, or both of them have the same chance, half-half. Okay, we already know this, right? Now, how do you get this? Why do we call that probability of getting head is half and probability of getting tail is the other half? How do you know that? Is it true that if you flip the coin twice, always one will be head and one will be tail? Can you get that? What do you think? Or if you flip the coin 4 times, is that always 2 heads and 2 tails?
No.
No, you won't get that. If you flip the coin 10 times, will you get exactly 5 heads and 5 tails? No. But how do we, then why do we say it is 50-50? How is this value, how was it calculated? How do you know that it is 50-50? Okay, so that is the law of large numbers. Okay, the probability is defined for the experiment which is repeated for a long run. Okay, that means you repeat it many times. By just flipping a coin 100 times, you will not get 50 heads and 50 tails. Okay, because that number is small. 100 is, it's not a considerable number to define probability. If you flip the coin, say 10 million, 100 million times, then you will see the probability of getting head is getting closer to half. Probability of getting tail will be getting closer to 50%. Usually it will reach, we don't say it is exactly, but it will reach the probability 50%. Okay, so that is why we call it the law of large numbers. Probability is defined for large numbers. That means you have to do the trial again and again and again, many, many times in order to find this probability of getting head is 50%. Okay, another example, if you roll the dice, okay, the 6-sided dice, again, we know if the dice is a balanced one, you know, all 6 sides will have the same probability 1/6. Okay, because that we say equal probability for all 6 sides. Getting a 1 is 1/6. Getting 2 is 1/6. 3, 1/6. Again, how do you prove it? If you toss or if you roll the dice 6 times, you will never get each side once. Never. Even if you toss the roll the dice 60 times, you can't say you get 10 ones, 10 twos, 10 threes. No, it will not happen. Again, you have to roll the dice hundreds of millions and millions of times. Then you will see probability of getting 1 gets closer and closer to 1/6. That is the law of large numbers, and that is how the probability was calculated. Not just doing a certain experiment 1, 2, 3, even 10, 100, 1000 times, even that is not enough. Okay, so probabilities are defined for large numbers, long runs of experiments. Okay, so you can try this. You can flip the coin a certain number of times and record it. Say, for example, this is something interesting. Okay, you note down your flip and whether you got the head or not. Okay, and then you find the probability of getting head. You can try this. Okay, say for example, here's your first flip, you got head. So this is 1/1. Okay, which means 100%. Then the second flip, you got a tail. So what is the probability of getting head? 1/2 now, which is 50%. Then you flip it third time. Now you again got tail. So what is the probability? 1/3. It's 33.3%, something like this. Fourth, now you got a head. So you have 2/4, which is 50%. Flip the coin, fifth, again you got a head. Okay, this is just okay, something I am just coming up, right? 6, you got a tail. Now you got 3/6, 50%. Okay, so likewise, so this will be 30 divided by 5, 60%. So likewise, you will fluctuate your value above and beyond 50%. And if you draw this, right? If you draw this, this is the number of flips. And this has the probability of head, getting head. Here's our 0.5. And you will see this value goes up and down like this. And eventually, after a large number of times after tossing it, you'll see that it attains the value 0.5. Okay, so you have to do many times to get this. Okay, and then you will see the probability of getting head gets closer and closer to this 0.5. Okay, so that is the idea of probability. Okay, so this is something just to give you the insight of how this probability is defined. Okay, right. So let's look at some axioms of probability. Okay, these are, again, you don't have to remember these things. Okay, just get the idea. Okay, so we are talking about an event A for a sample space S, and we define the probability of event A as PA. And look at these axioms. Okay, probability of A is always greater than or equal to 0. Okay, so this is something you should actually remember, because you cannot have probability is never negative. You cannot get a negative value because you count how many are there out of the total. The minimum you can get is 0. So that is why it says greater than or equal to 0. It can be 0 or more. Right? So probability is never negative. Then the probability of the sample space is 1. Why? You have a number of elements in the sample space divided by number of elements in the sample space. This is the definition of probability of S. This is 1, right? And then if you have events A1, A2, A3 up to many, can be finite or infinite. That means it can end at AK or AN, or it can go beyond. And suppose they are mutually exclusive, that means there are no overlaps. Then if you find the probability of their unions, they will be the summation of the probabilities. Okay, this one again you don't have to memorize. When you do calculations, you'll use it, but you don't have to memorize it or do anything, right? And another thing, I can add something else to this. You can write it like this. The other way around is better. Probability of A is always in between 0 and 1. Okay. So which means probability is never negative and probability never exceeds 1. Why is that? The maximum you can get is the sample space, right? So you cannot get a value for probability which is greater than 1. Okay. You cannot have negative values. You cannot have values greater than 1. Okay. So in order to, when it comes to axioms, we don't need to prove it. Okay, they are there. You have to admit it. Okay. Anyway, so look at this example. An experiment has 4 possible outcomes A, B, C, and D, and they are mutually exclusive. You know the meaning mutually exclusive. What is it? Mutually exclusive means they do not overlap. There are nothing in common. Okay. And you have given the probabilities. Probability of A, B, C, and D. Now you have to check whether these are correct probabilities. What do you think? Are these correct? Are these values are correct for a probability value? Okay, look at A. You have given the values of PA, PB, PC, and PD. What do you think? Is this a correct assignment of probability? Yes. When you say mutually exclusive, you can define the sample space something like this. A, B, C, D. Right? Mutually exclusive, they do not overlap. And when you combine A, B, C, D, you get the total sample spaces. Are these correct probabilities? 0.12, 0.63, 0.45, negative 0.2. Can you have negative probabilities? No. Right? Probability, I mentioned you, probability is never negative. It never exceeds 1. So none of them are exceeding 1, but there is a negative value. So the assignment of probabilities for these 4 events, it is wrong. Okay, so it is wrong. What about the next one? PA, PB, PC, PD. Now, if you look at these probabilities, all of them are less than 1. That is very clear out of 120. But when you add them, they should add up to what? When you add PA, PB, PC, and PD, what should be the answer?
120.
It should be the 1. It should be 1 because it gives you the sample space. When you add them, can you get 1? Can you get 120 or 120? What do you get? You get 7, 6, 8, 12, 127 and 420. Is this correct? No. If this is a correct assignment, you should get 120 or 120. But it is not. Although the probabilities are okay, when you add them, you get a value beyond S, beyond the total, which is 120. So again, this is not a valid assignment for the given experiment. Okay, right. Now here are few other operations you may come up with. A minus B. A minus B is the set of all the elements in A but not in B. Okay, so you can see the colored area, right? Everything in A but not in B. See, B is not touched. B circle is not touched. Okay, only A. So you can say this is only A. Another word to say is only A, and if you write it, it is A intersection B's complement. Okay, so this is same as A minus B. You can do the same for, you can interchange B and A, right? So you can do that. Then you say two sets A and B are equal if A is contained in B and B is contained in A. So that is obvious, right? So this circle is both A and B. So which means A is inside B, B is inside A, right? So that is both two sets A and B are equal, right? See, that's a Venn diagram, right? Then you have few laws, distributive laws. Again, you don't have to memorize them, but they are actually easy. See, what you have done is just changing the parentheses, right? It's the union. And then when you have the intersection and the union, you can distribute it. A intersection B and this union here and A intersection C. Then you interchange union and intersection. So you have A union B intersection C. That is A intersection B. Sorry, A union B intersection A union C. That is the distributive law. Then you have the De Morgan's law. So that was what we had in that example F and G parts. Right? De Morgan's law is you have A intersection B whole thing complement. You can distribute the complement and change intersection to union. See, A intersection B's complement becomes A complement and B's complement and change this intersection to union. Okay, can you see that? And do the same again the other way around. You have A union B whole thing intersection, then you, whole thing complement, then you distribute the complement, A's complement, B's complement, then the union becomes intersection. So that is called the De Morgan's law, right? Another thing, if A is contained in B, we say A is a subset of B, right? This one, you already know it now. A is contained in B, so here's B, A is contained. If you take the intersection of A and B, the overlap, what is the overlap? A itself, see? Intersection is A itself. If you take A intersection B's complement, what is this? Only A. Can you find something only A? You cannot, because A is inside B. So automatically a part of B is inside A. So that is empty, right? So those are about the subsets. Okay. This example, okay, let's try this one. Now you already know how to write the sample space and events. So let's try to calculate probabilities. This is very easy now. If we twice flip a balance coin, what is the probability of getting at least one head? Okay. If you twice flip a balance coin, you flip the coin twice. What is the sample space? Head, head, first head, second tail, first tail, second head, both tails. Here's your sample space. Flip a coin twice. Balance coin. Okay, so balance coin means the probability of getting head, probability of getting tail, they are same, 50-50. Since we assume the coin is balanced, all these outcomes are equally likely. So when you say equally likely, what does that mean? All four outcomes have same probability. How do you get that? The total probability is always 1, that is the 100%. So you have to divide 1 equally among all possible 4 outcomes. So it is 25%. So getting 2 heads is 25%. Getting one head, getting the head and tail is 25%. Getting tail and head, 25%. Getting 2 tails, 25%. Okay, so that is what you call equally likely. The total probability is always 1 or 100%. You divide it equally among all possible outcomes. Since there are 4 outcomes, you divide 1 by 4 or 100 by 4, so 25%. Okay. So what is the event that you want? Getting at least one head. Okay, so that is our event A, getting at least one head. So let's find the getting at least one head first. Okay, so here's the sample space. Getting at least one head, what are the outcomes? At least one. Least you can get is 1, or you may get more. So how many outcomes are there? 3. So what is the probability of A? This one has 1 over 4, this one 1 over 4, this one 1 over 4. So what is the value? 3 over 4. And if you think about the definition of the probability, what is this? Number of outcomes in A divided by number of outcomes in the sample space. Right? So how many outcomes are there in A? 3 outcomes. How many outcomes are there in the sample space? 4. See, you get the probability of A. So this is very easy. If you can find the sample space correctly, if you can list down your elements in whatever the event correctly, then the probability of finding the probability of that event, it is just the number of elements in that event divided by the number of elements in the sample space. Okay, is this clear? Any question about this one? Okay, let's try another one. Say I'm going to define another event, right? My event P is getting same outcome for both flips. What is B? And then find probability of B. Yeah. Getting the same outcome for both. What is B? Will be head or TTS. So how many outcomes are there in B? 2 out of total 4. So you can write this as 0.5 or 50% or 1 over 2, or if you leave 2 over 4, either is, all these answers are correct. Okay. So it's up to you. If you want to leave it as a fraction, that's fine. As a decimal, that's okay. As a percentage, that's also okay. Okay, no problem. Right? Okay. Right. And here's another rule that we usually use. That is called for the complement. If A and A's complement are complementary, okay, you already know that. In the sample spaces, if you want to find the probability of A's complement, that will be 1 minus probability of A. Why is that? Because the complement is everything in S but not in A. So this is same as you get the sample space and subtract A. So that is the complement. This will give you the I'll write it in a better way. You take the sample space and subtract A, then you get A's complement. So when you take the probability, you get probability of S minus probability of A is the probability of S complement. But you know probability S is 1. That's the total probability. So you get A's complement, that probability is 1 minus PA. Right? So if you go back to this example, PA is 3 over 4. What is what is the probability of A's complement? If PA is 3 over 4, what is probability of A's complement? 1 minus
1 over
3
4.
over 4. Yes, that is 1 over 4. Right? So this is not something hard. Right? And this is correct because A and A prime are mutually exclusive. Okay, you can, when you have the negation, they do not overlap, they cannot. So they are mutually exclusive, right? And then if you have an empty set, then the probability of the empty set, well, it is obviously 0 because there's nothing inside, right? And when you have the subsets, if A is contained in B, so probably when you calculate the probabilities of A and probabilities of B, the probability of A should be less than or equal to probability of B, right? Okay. And next comes the something important, the addition rule. Okay. Addition rule is used to calculate the probability of a union. Okay. So this is to calculate the probability of a union. The probability of a union is the probability of A, probability of B, subtract the probability of A intersection B. Okay, so this is called the addition rule. Right now, this one, well, usually you can remember it. Now you have already used it from your school time. So this is nothing something new, right? So you already know this. Okay. So the union of two events, you add the probabilities of those two events. And when you do that, the overlapping area, you count it twice. That is why you subtract the intersection once. Okay. This is the addition rule. Okay. Now keep in mind all the rules and axioms we have learned so far for probability. Let's try an example. Okay. Let's try an example. Right. Before we do that, shall we try this one? Okay, let's try this example. Among 100 patients registered in a clinic, 60 suffer from diabetes, 45 from heart disease, and 15 from both. Okay, so you have 100 patients registered in a clinic, 60 suffer from diabetic, 45 from heart disease, and 15 from both. You have to find these following probabilities, right? So when you get a question like this, it's easy if you draw the Venn diagram. If you can do it by just assigning the probabilities, that is also okay. Say, for example, we define D for diabetic, HD for heart disease, and so on. And if you can find the probabilities, that is also okay. But it's easy if you draw the Venn diagram. Since it says 15 suffer from both, that means there is an overlap. So let's draw the diagram like this. My first circle is for the diabetic patient, second is for heart disease. Okay. Now shall we fill these circles by the count, right? So when you fill diagrams like this, you always start with the overlapping area. It says 15 suffer from both. So 15 should go to this intersection area. Okay. Now let's go back and find, say, 60 suffer from diabetes. So this whole circle should contain 60. Out of this 60, already 15 is there. So what should go here? Only D. What is the value that should go into only D, this area?
45.
Should be 45. So 45 and 15, you get total 60, right? Now let's go to the next one. Heart disease, there are 45. Out of 45, already 15 are there. So what should go for heart disease only? It should be 30, right? 30. Now count this and see whether you have all 100 patients. This circle contains 60 and then another 30. 60 and 30 is 90. Or you can count, add 45, 50 and 30, which is 90. So where's the rest of the 10 patients? Where are they? Okay, those are the patients who do not have diabetic, they do not have heart disease, none of them. So where do you put them? Outside the circles, but inside the sample space, right? So those are the 10 patients who do not have either diabetic, neither heart disease. Okay. Now you have all 100 patients inside that rectangle sample space. Okay. Is this clear to all of you? Right. Now it's easy to calculate the probabilities. What is the probability diabetic only? Diabetic only, where is this? Diabetic only is this 45, right? It is 45 out of how many? 100 patients. So what is the probability? 45%, or you can say 0.45. Okay. Now what is the probability heart disease only? What is that probability? Heart disease only is this area. So what is the heart disease only? It is, yes, 30 over 100. 30% or 0.3. Okay. Diabetic or heart disease. What is that?
90.
That is the union. That is the 90. Great. 0.9 or 90%. None of them?
10.
10. This 10 is the none of them. So you have 10% or 0.1. Is this clear to all of you? How to find the probabilities? Right. Any question? Okay. So with that, I'm going to do an in-class group assignment. Right. So very similar to this Venn diagram, very similar to this example, 100 patients. Now this one has 3 events. So you have to draw the Venn diagram for 3 events and fill the blanks and answer these questions. Okay, fill the Venn diagram and answer these questions. So I'm going to stop the sharing for a while because I'm going to break the room. Okay, I'm going to break, how many are there? We have 32 participants. Okay, so I'm going to break out them. How many into, let's say, 4 into room. Okay, so this is done automatic. 4 rooms, 8. 8 is too much, right? Let's see. Let's make 6 rooms. Okay, so I have created 6 rooms. Okay, you have been assigned to 1 room. First room contains 6, second room contains 6, third room contains 5, fifth room contains 5, fourth room contains 4, and sixth one contains 5. Okay, can you see this breakout? Okay, I'm going to open the rooms now. Okay, did you get the invitation to join the room? Okay, please join your room. You got the invitation. Okay, now I'm not inside any of your rooms. Okay, so you can talk among yourself and find the answers to these questions. And I'll give you 15 minutes. Find the answers and let's try to check your answers. Okay. Right. So you can unmute yourself. Okay. Nanduni, Takshila, you have not been assigned to any room. I'll assign you to room number 4. Okay. Okay. Room number 4, Nanduni, can you join to room number 4? Right. Okay, so can you start working now? So once in a while, I'll come inside your room, okay? And check whether you are working. So you can unmute yourself in room 1. So those who are in room 1, can you hear me?
Yes, madam.